computer. Okay, so we are now doing a new topic. We learned about opening files, closing files, reading files, writing files. We write them with regular primitive read and write. We can write them with the more advanced there's F open and F close and F read and F write. We learned mostly F read, I think. There's also F write. All right. Now we're talking about a new topic, which is creating processes. This is an important thing because we talk all the time in operating systems about, process, what happens when a process is made. A new process gets made. Well, the basic way of creating a process is by running a program. The minute you run the program, now that's a process. But you can also have the program itself create another process so that you could have what's called a child process. In other words, one process creates another process, and then you have multiple processes. This can be dangerous if you do some kind of infinite loop. You'll make many, many processes and the computer will freeze up. So be careful with this. But there's a basic command called fork. And fork does what I said. It creates a process. It creates a child process that differs from its parent process only in its process ID, parent process identification number, and in the fact that resource utilization are set to 0. In other words, it doesn't have any resources. File locks and pending signals are not inherited. That's a key point. Like if there's a signal that hasn't yet been sent but is in a queue, it won't go to the child. The child won't get that queue. It'll have a fresh, clean signal queue. A call to the fork system call returns 0 to the child process and returns the child PID to the parent process. This is a very complicated and important point. That's why I wrote it in bold. Again, when you call the fork system call, a 0 is returned to the process that's the child, and the parent will get the PID of the child that got created. So let's see an example right away. So for example, I make a variable called A, and I give it the value 9, and that's this random name, random value. And I make another variable called PID of type PID type. Unix is a little bit quirky. It has all these types that are really just integers, pretty much, or sometimes they're not, sometimes they are, but a lot of them are just integers, and they give them special names. I'm not 100% clear why, but it's a PID type for storing a PID, a process ID. So now I call fork. And what happens here? The minute I run this function, fork, the program splits, it forks into 2 programs. One of them we call the parent and one is the child. But what happens is this fork returns, it's as though this fork, since I created at this moment 2 functions, it's going to return 2 values. And the PID in the parent will get 1 value, and the PID in the child will get a different value. So when I get to this line, print my value, both programs will reach this line, and they'll each print a different value. Now you want to see an example of that. Let's do a share here. And let's see if I'm still connected. Am I still connected? You see my black screen? But it looks like
And we see the screen.
You see the screen, but I can't do anything on the screen. So let me try that again. Just a minute. All right. Second, I'm just typing something. Oh, again, I froze up.
Computer's frozen?
Oh, no, my connection to Machon Lev froze up.
You're using remote access?
That's what I'm saying.
You don't have it on your you always been using remote access, or you're using your home laptop?
Oh yeah, I use my own laptop. It's just, it's not going to work because I didn't try all these examples on my own laptop. Whatever, I won't show you the examples. Sorry, but you'll believe me when I just tell you what they say. Share screen. I keep forgetting to set up my computer. You know, because this class is on Thursday, and then don't feel like going right to work, and then it's a weekend. So you see my screen, yeah? Do you see my screen?
Yeah.
Okay, so my value is going to print, but Kitzer, it's going to print two different numbers on the screen. It's going to print my value of PID twice, followed by a number. One will be 0 because it'll be the child, and one will be the parent who's going to print the child's PID. So is that clear? I hope. Here's another example if that wasn't clear. Now here I ran the fork. I don't want to always see, the problem in this program is that both people wrote this thing. But what was the point of my fork? Usually when I do a fork, I want the child to do one set of actions and the parent to do a different set of actions. So the way I do that is with an if. Since I know that the fork will return a 0 to the PID if it's the child, I can check for that. And I can say if PID equals 0, then I know I'm the child. And I can print some message as a child. Else, if it wasn't 0, then I must be the parent. I am the father. I don't know my own PID, but my son's PID is a %D and then PID. Well, PID is that value I got over here. Because if it was 0, I would have been over here. So it's not 0. I must be the parent, and I have the child's PID number. Does anyone want to ask me something about that?
Yeah, we've technically, when we learned C, we basically started with C++. So I'm just wondering if this printf statement, is it comma separated? Because there's just a comma between the first part and the PID.
Printf can be run. It's a weird kind of function that you never saw before because at one point I learned how to do this, but I don't remember now. But you can write a function in C or C++ that takes a variety of parameters. In other words, this an infinite variety of parameters. And as you know how to do like overloaded functions, but here printf can take just a string, or it can take a string and followed by a comma, and then any number of variables, and then those variables will be printed wherever there's a %d or %s. So in this case, I have only one, so I have 1%d and one number. But it's a function. The function takes two parameters. One parameter is this long string, and the other parameter is this variable. But actually, printf is declared as a function of unlimited number of variables. Avram, you know how to write a function like that?
No.
Okay. Well, you don't have to know. For this
I mean,
course, you
I
don't have
do
to.
it in a.
You could learn in 10 minutes because you would just Google, how do I write a function, in C that has a unspecified number of parameters. You've never done that.
Number of parameters. I thought you said type of parameters.
No, number of parameters.
You could do a list.
Yeah?
And then,
No, that would be a single parameter of a special type, like a structure, you're saying, or a class list. No, I don't mean that, because this is not a list, this is an integer.
Isn't it kind of what's always done like at main usually? You take a
No.
No, that takes a string.
Main has
Oh.
two parameters. Argv, which is a string of strings. It's
Yeah,
a
yeah,
two-dimensional array, and argc, which is an integer. No, this is different. This is a different thing. It's not taking a variable that. Oh, but you're kind of right. I mean, argv, it's 2 pointers. Whatever. No, it's different. Argv is different. That's a single variable, which is an array. This is not an array. This is actual numbers. And comma separated. Normally, parameters of a function, you have to write int. This one not only is the type, the type is also not defined. Because I could write a type %s, and then I would write a pointer over here. So this is a really weird kind of function that you guys don't know how to write. And you can look it up, how to write such a function, which takes parameters of variable types and variable number of parameters, and undefined. Very weird. But it's doable, because it was done. An example showing that multiple calls to the forks creates more processes by a factor of 2. Okay, so look at this one. So we got this one. First of all, I can differentiate the parent from the child by what the fork value it returns, or the fork function returns. What about this one? How many times will it print hello, and how many times will it print bye? This one you have to write out on paper and think about it. So I'll give you a few minutes to think about it. I mean, look here. I got a fork over here and a fork over here. How many? So this is going to make 2. And then each of those 2 is going to see this line and make 2. So how many functions will I have?
5 functions.
I mean, not functions. How many processes will I have?
5.
Anybody have a different answer?
It's gonna be the root, and then each one's gonna do 2 child fork.
Well, how many did I have here?
Wait, when you fork, does it make 2 new ones or 1 new one? I forgot.
Well, look at this example. That's why I'm showing you this example. How many did it make here?
2.
Oh, so it makes one new fork. So it'd be 3.
Wait, so the fork, this is the original one. The fork just makes 1 more. So now there are 2. There used to be 1. Now there are 2.
So it'd be 3. And it would print it 3 times.
It's not, well, print what? How many times would it print bye, and how many times would it print hello?
It'll print hello once. And
When? Okay. When will it print hello?
at the end of the forks.
But no, but it's an in and if. It's only in and if. It's only when the fork equals the fork.
But they will equal. Oh, they return different PIDs.
Right. Well, this one returned different PIDs, right? Each one creates
So
its
they
own.
won't equal each other.
Maybe it'll never print.
No, but the childs will both have those equal each other because they're 0. Won't they?
Yeah. Well, that's what I wrote here. When will hello be printed? When a son has a son. Why? So let me get a pencil here. Second. Stop the share. Somebody want to run this program? Maybe Abraham? Here, let's go like this. This fork, the first fork, what will number be here? Well, the first fork, there'll be 2 numbers here. There'll be like 0, and there'll be some PID.
What do you have to include for fork?
Do man fork.
All right, that's a good answer.
All right, so you see this, that you see this, that on this side, I have a 0 by the child and a PID 1, let's call it the first PID, by the parent. Now, both of those guys walk over here and run this fork. So this guy will now create a fork, which means he'll create 2 functions. One will be the parent, and he'll get PID at 2. That'll be the parent will get that number, but the child will get the 0. Now this guy, the father, will go over here and he'll also create 1. He'll create, the father himself will get PID of the child. So let's call that PID 3. And he'll also get, for the child that he created, will get the value 0. So if you look at this, is PID 1 equal to PID? So over here was PID was the first values, 0 and the PID 1. And over here were the 4 values that are at the end after I created the 4 functions. So the four processes. So fork will be, so by the parent, the left side will be PID 1 and the right side will never be PID 1, so it'll never get to hello. But by the child, he originally, his PID over here was a 0. And then when he created a child, he got that child, so that won't work. But his child will get a 0. So the child's child will be the one to print. The child's child, when this is the child, and then he has a child, that child will also get a 0. I'll have a 0 here and a 0 here. It'll only print hello once, but it'll print by 4 times because there are 4 functions. There are 4 processes.
I got 5 lines with hello on the 4th one.
You should get 5 lines, exactly. 4 of the lines should be by, and 1 line should be hello.
But why is hello?
The order is indeterminable.
Because it's just kind of how the
It's how the operating system decided to context switch between them. Theoretically, if you
I
ran
just got
it,
one. I just
you
got
ran
one
it-
on the 3rd.
right, you could get it any I mean, the hello could be at any location, put it that way. Could be the first thing printed or anything after that. It's impossible to know. Unlikely, though, that will it be the first thing. But it's possible.
Wait, could you go over the tree again?
Well, this on the left side here, this fork. So he'll produce either a PID 1 or a 0.
Mm-hmm.
Because if he's the child, he'll get a 0. And if he's the parent, he'll get the PID of the child, we'll call PID 1. Now, each of those guys, they come over and see this right side of the equation, and they say, oh, it's a fork there, I better do that. So they do the fork, and that means this child does the fork, and he gets a PID 2. He gets the value of the PID of this child. But this child doesn't get that value. This child gets a 0. Now, also over here, this PID 1 walks over here, and he runs the fork also. So he himself will get the PID 3 of his child. But his child won't get that. His child will get a 0. So now I've got on the right side these 2 values and these 2 values. But on the left side, I've got these values. So when are they equal? They're only equal. Well, the PID is never going to be equal to PID 1 will never be equal to something on the right side. But 0 will be equal to the 0 over here, which is when the child had when this child had a child, his child got a 0. So that it'll be, they're both childs.
When you write fork, it will start from the beginning of that line that it was written on.
Yeah. Well, if there was a semicolon before here with some other thing, it won't do that.
I mean, the statement that it was on.
Yes.
It doesn't continue from after the fork. It starts over the beginning of the line. Like the new.
Oh, when this fork goes, it doesn't go and do that fork. No, there's a Seder of evaluation that the computer follows. It doesn't repeat a line ever. So unless it's a loop, but it comes here, it executes this, and that's it. It's never going to go back. When the program can.
But how does the son know what to do?
What?
Yeah, where does
How
the
does the
second
son know what
process?
to do?
Yeah.
Well, there's
Where's
two
it getting-
processes.
where's it
The
getting
minute
its
this
data?
fork executes, there's a child process and a parent process. They both then execute the right side of this equation. Because that's the Seder of operation.
So they only start
From wherever
following
they
the
were
function
created.
call.
They never go back in time. They
Mhm,
only
okay.
start from where they were created. The only reason, like, no, sorry. In this example, for example, this PID is created once. The reason why the second guy gets it is because he inherits all the variables that were created. He doesn't go back up and start from the beginning. He just inherits any variables that were created already. In other words, both of these guys will have the value a equals 9. Because the minute this fork occurred, all the variables that have been defined are continued to be defined with the values that they had. It copies the whole program, but it doesn't run the program again. If there was a C in or a C out over here, it wouldn't go back and run those. But if there was a C in and C out, and in the C in, the guy made value A equals 17, then A will be 17 for both programs. All the variables will have the same values.
The only
Until
thing
I
differing
change
is
one
the
of them.
PID.
What?
The only thing differing between the two forks is the PID.
Yeah. But then once I go like this, if I'm in the sun, I can change A to be 16, and this guy can change A to be 12, and there'll be two different A's. In other words, I have inherited the variables and the values, but from then on, I can manipulate them as I choose, and what one does will not affect the other. They're not the same variable, they're just two instances of a variable called A. But their initial value, but they were right. In other words, everything that
Is it-
happened up until then is still valid in both programs. I don't go and rerun though the beginning.
Is this the only way to create a new process? There's no other
Yeah.
way?
Well, there are some other ways. There's something called popen, but that doesn't really create this is the only way to create a process purely. There is, I don't know if I teach it. I did in the past. I don't know if I included it in my slides here. Maybe I did. There's something called a thread, pthread, how to make threads, which are not the same as processes, but they're quite similar. All right, creating a pipe with the command pipe. So what is a pipe? I'll explain it. Well, nobody ever explains it, but I'll explain it. Nobody ever explains why you want a pipe. A pipe is like this. A pipe is basically like a file. Like, let's say I have two processes. I just have these two processes. And I want that like one of them will write to a file and the other will read from the file. One of them's job is to compute numbers or I don't know what, and the other one's job is to read those numbers and do something with them. There's two different processes that have different jobs, but they need to pass data from one to the other. So the simplest thought might be open a file, one writes to it, the other reads to it. That's all very well and nice, and that will work. But I may say, well, why bother creating a file and using the disk and then having to delete the file? And maybe there's no space on the disk, maybe it's full. I just want a file, a virtual file, a file that only exists in memory. Because and the minute I close it, it's automatically deleted. I don't have to go and do a RM command on it. It's a file with I open it. I don't open it on the disk. I just open it in memory, and I use it. And then whenever I'm finished writing to it, the reader sees that I'm finished writing to it. He reads everything that says there, and then it's gone. So it's like a virtual file, but only for the purposes of writing from one program and reading from the other, from one process, and reading from the other. So we call that a pipe because it's like a water pipe. The water rushes through the pipe from one, the water being the data, rushes through the pipe from one to the other. And the minute that, the pipe doesn't hang around once the water is gone. So that's the idea. So pipe creates a pair of file descriptors. So a little bit more complicated than you might think, because since it's specially designed for reading and writing by two different people, it's going to have two file descriptors automatically created, one for the reader and one for the writer. And we pointing to the pipe inode. Inode just means like it's either a file, and places them in the array pointed to by file descriptor. So let's see the example before I continue. First thing I do is I create two file descriptors, essentially an array of file descriptors, 2 integers long. So FD is a pointer, and it has a place 0 and a place 1. And then I pass FD. I like to call it, most people call it FD, but I like to call it actually PD, pipe descriptor, but it's a kind of file descriptor. So FD is good. FD with the pipe. In other words, I say pipe, means create a pipe. It's like open a file and give it 2 integers that are blank, but I'm giving a pointer to the integers. So what it can do, this is a very clever little thing in C and C++. Let's say you want to return two variables, right? A function only returns one variable. But in this case, I need to return two, a file descriptor for the read and the write. So how do I do that? So the answer is I give a pointer, and the pointer will point to an array, and the array will be blank. But when the function gets this pointer, it will write something into that array. And now when I use FD, it actually has a value in it. See, I write to FD1, but what value is in there? I never put a value in FD1. I just created a blank array. When did that happen? The answer is pipe has like a side effect. Well, it's the main effect that it's supposed to have, is that it writes to FD two numbers, like 4 and 5, whatever the next two free file descriptors for that process are, it will write them into this array. So let's go back. So it creates a pair of file descriptors, places them in the array pointed to by file des. See, that's this file des, file descriptor array of 2. Notice the prototype is Dafka 2 numbers, not an array of undeterminate size, but exactly 2. And what will happen is like this. File descriptor 0, the first one, is the read side of the pipe. That's the guy who's going to read. And why did they choose 0? Because the same as stdin. stdin is 0, which is where you read from the keyboard. And file descriptor 1 will contain the value of the file descriptor for the right side of the pipe. So you'll write to file des 1 and you'll read from file des 0. On success, 0 is returned. On error, it will return an int of -1. The pipe has two sides. The 0 side refers to one end and the 1 to the other. And like I said, always write to the 1 and read from the 0, just like you would read from standard in, which is 0. Important note, when one writes to a pipe, it may be open for read as well. You can write to it even though it's open for read. I'm writing and the guy is ready to read. But when reading from the pipe, we must remember to close the right side on both processes. Everybody, you have to, in other words, it's really a one-time write and read. It's not a continuous water pipe. It's a water pipe where you write into it as much as you want, and then you close it, and then you read from it. And then you're done. It's not meant for like a continuous flow of data. It's meant for a one-time write and a one-time read. But, all right, I want to take a 3-minute break right here before we get into the examples. So I'm going to pause the record. Okay, so let's look at this example. Let's look at this example. In order to create a set of pipes, a set of pipe file descriptors, we will call the pipe function. In our example, we put a simple string into the pipe and then read it out character by character. We could have read it out not by character, but the whole thing at once, but we're going to read it out character by character. So file descriptor 2 has hello friend and character ch. Fine, that's going to be like our buffer, the ch. And then we say pipe file descriptor, and create pipe requires array of 2 integers. Like we said, that's an array of 2 integers. FD is 2 integers. So now we have our pipe. And we don't have actually any, we only have one process here. We're just writing and reading ourselves. So we've created our pipe. Now we do write to whatever the number in file descriptor 1 is, which is going to be the number referring to the right side. And we're going to write into it with write command, which write always uses 3 parameters, which is where to write, what to write, which is the string, and how long is that thing. So we use string length of str. So I don't have to count how many letters it is, but hello friend is whatever it is. And That's what I'm going to write into the pipe. Write the string into the pipe. Now we close the read side to indicate that I finished reading. If we don't do that, the read won't work. It'll wait for me to close it. So I close it, I finished writing. Now I read from the pipe, and I do it in a loop while read. Now remember, read will return me 1 every time because I'm reading exactly 1 character, which is true. And then eventually it'll get to the end and it'll read nothing. So it'll return me 0. So this while loop will continue. And what will it do? I'll print each time the character, CH. %C is when you want to print a character. You call it C for character. And then I do a loop as many times as there are letters in this array. I finished writing, I print a new line, I close the read side because I'm finished. And there I've written to the pipe and read from the pipe. That's not very useful, but that's just the most basic way of using it. Now, a more complicated way of using it, child process writes via pipe to a parent. So we want to have communication between the child and the parent. So that's the whole point. We created pipes. We learned pipes to create child and parent. Now we want what's called IPC, Inter-Process Communication. And one method of inter-process communication is with a pipe. So we create our pipe again, and now we do a fork. Now it's very important that first you create the pipe, and then you create the fork, so that both children will have the same pipe. If I would create the pipe after I did the fork, what would happen? Somebody tell me what's wrong with that?
Only one of the processes would have the pipe.
No, both. No. If I would just immediately, if I would just write here fork and then
Oh.
write pipe.
They would be different. They would be different pipes.
Exactly. Each process would create a pipe, but they would be different. There was no connection to each other. I want to Dafka create one pipe. Now what happens is the FD here, this array gets duplicated. Both children will have an array. And the values in them, though, will be identical. So they both will, and that the pipe won't get duplicated. Why won't the pipe get duplicated? If I did a fork after I created a pipe, surely everything that happened before gets duplicated. Why doesn't the pipe get duplicated? Anybody answer that? Aside from saying, well, it just doesn't. I mean, that is kind of the answer. Any ideas? Why would the pipe not get created? Remember, what is the pipe in place of? What is it? A virtual what?
The pipe is just some shared memory. It's not actually part of the memory of that program.
Right. It's a system resource. It's called a system resource, like a file is a system resource. It's external to the program. It's some external memory that has been assigned for the use of this pipe. So I'm not going to duplicate. That would be like if I opened a file and then I did a fork. I'm not going to have 2 files now. I only opened the variables that are in the process, not the system resources that are allocated to the process. System resources are actual physical things in the real world. I'm not going to duplicate those. I'm just going to duplicate a file. It's like a file. I'm not going to duplicate the file. I'm only going to duplicate the value, the variables, which is this FD. Okay, so now I've created a fork and I've got the PID. And look, I do a clever little thing here. Instead of doing if to see if it's the child or the parent, I do a switch. Now I'm doing a switch on the PID because fork will run. It'll assign PID a value. And then I will switch based on the value that PID got. So if the switch is case 0, and as if PID is 0, then I'm the child, and then I will do this. And otherwise, I do default. In other words, I'm the father. I don't know what PID will be for the father, but it will not be 0. There's one mistake here. I should really check first for case. What case should I check for that I didn't? Anybody? What case did I not check for? Let's look at the man here. Oh, it doesn't say. Did I say here? What case did I not check for? I did not check for failure. Theoretically, it could fail to create a fork, in which case the PID would be -1. So I really should have had a case -1, if in case, and then error, exit the program. And otherwise, if it's 0, that, and then default anything else, it must be the father. So let's look what the child does. The child does close the read side. So he closes the read side. Because FD, he is not interested in reading. The child is going to write to the parent. So he closes the read side, and then he goes to the write side, and he writes, hello, father, and 13 letters, and he goes into the pipe, and then he closes, very importantly. This closing of the read was not that important, but the closing of the write is very important. He closes the write side to indicate that he's finished writing. Now break. Break will take me out of the case switch, and essentially the child is finished. He's done. In other words, he'll go out of the case switch and he'll exit. Or the switch case. Now default, I'm the father. So the father, he closes the right side because he's not interested in right siding. Now, if I don't close this right side, the father will never die because he will wait around waiting to write. In other words, the read won't work because he'll think that somebody is still writing because there's still one open write. So he won't actually do the read. The read will pause. He's sort of being very polite, waiting for the person who wanted to write to finish. Because remember, you always do write and then read because you don't read from a pipe before you wrote to it. So if he, even though the child closed the right side, the father also needs to close the right side. And then he'll be able to read. And I do a while loop while the read is not 0. Then read one character at a time. I just chose to do one character at a time. You could read more. And I do a loop and I keep reading, printing out. F flush is a special function, means file flush. And I'm flushing to stand it out because sometimes when you print something, it like waits for some more letters to build up and then it prints it all at once. But if I want to force it to print right now, then I do this F flush. And then I close. So here we see a simple case where the child wrote to the father and the father read and printed and exited. Still not very useful, but you see the idea that you can have two processes and they can communicate. And that's the basic idea of what we call inter-process communication or IPC. That's enough of pipe. We'll use it more later maybe, but that's enough pipe. Now, another function. All these functions we're going to use, why are we learning all these different functions? I mean, this is some of the major important functions of the operating system. That's one reason. But also, using them will help do a certain targil, a certain homework assignment that I want you to do, which is to write your own shell. Or at least a basic form of the shell. It's not a real shell. Not a shell that understands language, but just a simple shell to run program, to run commands. So, and all these functions are needed for that. So dupe. Dupe is an interesting little function. What it does is, we talked about file descriptors. So dupe is a system call that creates a copy of a file descriptor using the lowest numbered unused file descriptor available. So for example, I go like this, open a file, and I opened it with whatever flags I wanted, whatever mode I wanted, and I say duplicate FD. FD is what I got back. So I have FD copy. Now I have two file descriptors, FD copy and FD, that both point to this file. So whatever number this is, this is a different number, but it also points to this number. In other words, this FD is, let's say, 4, and this FD copy is 5. So they're different numbers, but they're pointing to the same file. It's a duplicate of whatever this was pointing to, but it's a different file descriptor. It's like I have 2 pointers to the same file. Now, FD is, so print, FD is this number, and I give it, notice here I gave 2 numbers I want to print. FD is D, and FD copy is D, is decimal. So FD and FD copy, I'm going to print what numbers they are, and they'll probably be something like 4 and 5. Now I close FD, so the original one is closed, just to show that closing the original one does not close the copy. So now I do write to the copy, and I don't get an error. It'll write new data to that file. If I would open the file, I would see new data there. So that's just to show you the point. Now, why didn't I close FD copy after this return or before this return? Why didn't I close it? The answer is because everything gets closed when the function ends, when the process ends. You're not going to have a dangling, open file. Once the process ends, it closes automatically all the files. So I don't need to close it. I could, won't hurt. I don't need to. Either way, the operating system will close it. But I didn't read everything about this. On error, it returns -1, like we usually see. Right, new file will be 3, and I'll have all the attributes of the other one. Okay, so I could also run it like this, by the way. I could actually write the number. As in my example, I wrote a variable. I wrote FD, but FD is just a value. So I theoretically could write it like this, with just a number. Dupe example. Notice that, okay, so here we're getting, I want to combine fork. Do I use pipe here also? And pipe and dupe all together. See, we're getting more and more pieces of this puzzle. Notice that I have to close the standard in and the standard out in order for dupe to return me the low FD, either SD out or SD in. Otherwise, dupe would return me 4. Okay, let's see what I'm doing here. First thing I do, I create my pipe pointers. Then I create my PID, and then I say pipe on the pointers. So now I have a pipe. Now I say fork. And here I do check for, by the way, I don't do a variable here. I don't have to assign it to a variable. I just do fork here inside the variable. Now fork will return me a number, depending on which process I am. If it's an error, it'll end. If it's not an error, then it'll be a child or a parent. So if it's the child, I'll do close the pipe. So I closed which side of the pipe? The read side, because the child is going to be writing this time. So I close the read side. I also close 1. 1 is, what is 1? 1 is writing to the screen. So I close 1. Now when I do dupe, this is a little bit tricky. When I do dupe of the pipe, what am I doing? What number will dupe return in this case? Can anyone guess what number dupe must return here? Remember, we had like this. Here I did dupe and I put it into a variable. But even if I don't put it into a variable, it will return a number. It just will, I won't have stored that number anywhere. But if I'm super genius, then I know what number it's going to return. I don't need to store it anywhere. What number will this store? Will this return? No. What does dupe do? What numbers does it return?
What, 0?
Well, 0 is already tafus. The 0 is already taken up by the standard input, by the keyboard. So it can't return the lowest number would be 0, but it's not going to use that one.
So it's 2. 2.
Because 1 is taken up by the, but I closed 1. What does it mean to I close 1? What does that mean, close 1?
You're not writing to the screen anymore?
I'm saying file descriptor 1, which is pointing to the screen, is now free, is now available. I'm no longer going to use 1. If I want to point to the screen, I'm going to have to use 2, because 2 also prints to the screen. It's error, it's standard error. But I'm not going to use 1 is detached from the screen. 1 is a free agent at this point. I closed it. It's like a file. Remember, the screen is like a file. So everything is a file. So I closed 1, so now 1 is available as a file descriptor to point to anything in the world. So what is dupe going to do when it sees this line? What is it going to do here? Remember, it's going to duplicate a pointer to this pipe, to the right side of this pipe. And what value will it assign to that? Not the value that's here. The value that's in this array could be like 4 or 5.
If it was already free, will it return -1?
No. Why -1 means error? It's not going to be an error. Well, if I would draw the table, if I would draw the table of file descriptors, it originally looked like this. You know, 0 is the screen. Sorry, it's the keyboard. 1 is standard out to the screen. 2 is standard error. 3 is going to be the read side of that pipe, presumably. I mean, it could be the read or the write. The read side of the pipe. And 4 will be the right side of the pipe. That's what it will look. That's what the file descriptor table, those are the numbers that will be assigned. I didn't write out what they're assigned to, but I said it orally to you. This is the screen. Again, sorry, this is the keyboard, the standard output, which is the screen, the standard error, which is the screen. The 3, which is really going to be this, which is going to happen when I do this pipe. The PID 0 will be 3, and PID 1 will be 4, pointing to this pipe. Now, when I come here and I say close 1, what happens? I close this. That means this 1 is no longer pointing anywhere. It's unassigned. Just like the 5 and the 6 and the 7 and odd 60,000 are all not assigned, or 32,000. So when I go to dupe, what's the definition of dupe? It says that dupe always assigns file descriptor, the next available file descriptor, to whatever this file descriptor is pointing to. So what is this file descriptor pointing to? It's pointing to the pipe. So what number will it assign also to point to the pipe? The next available one. What's the next available one? Well, some of you might say 5 is the next available one. But really, what is the next available one? No. It's 1. No, you don't see. No, do you understand why it's 1? 1 was previously removed from the table, and when I do dupe, it goes through the list and sees the first hole that it finds. And the first hole it finds is 1. So 1 will now point. It'll return the value 1 over here. It's as though I wrote 1 over here. As it returns 1. It returned a 1. Now, what does printf do? Printf prints to 1. It prints to the screen. It doesn't know that 1 is no longer pointing to the screen, but is in fact pointing to this pipe. So when I do printf hello user, it actually won't go to the screen. It'll go to the pipe. Is that clear? Printf is a dummy. He just knows write to file descriptor 1. Well, file descriptor 1 is pointing to whatever this pipe is pointing to, whatever this number is pointing to. This number is pointing to the pipe, so 1 is also pointing to the pipe. Is this going over your head? Well, we're finished for today, really, even though we had some breaks. We'll stop and we'll continue there from there next time, okay? It's a little bit, now it's getting interesting, so it's harder. Easier for me and harder for you. You guys still there? Am I
Yeah, why is it easier for you?
Because it's easier for me because it's interesting. It's
Oh, I see. Okay.